Hello students, welcome to our student support program for grade 11 additional mathematics. Today you are going to learn how to apply differentiation to kinematics problems that involve displacement, velocity and acceleration of a particle moving in a straight line with a variable or constant acceleration. So let's begin. In additional mathematics, you should already know about distance time graph and speed time graph. Distance time graphs can be used to find out how the distance changes with time. The gradient of a distance time graph, that is change in distance divided by change in time, represents the speed. Now let's study the graph in detail. The graph has three parts. First part, from time 0 to time t1, a straight line graph represents constant speed. The second part, from t1 to t2, a horizontal line graph represents speed is 0, that is, no movement. The third part is a straight line graph with steeper gradient means speed is greater than the first part. Next we have speed time graph. In a speed time graph, this can be used to find out how speed changes with time. The gradient of a speed time graph represents the acceleration. Let's study the graph in detail. The first part, from time 0 to time t1, a straight line graph with positive gradient represents constant acceleration, that is, speed is increasing. The second part, a horizontal line graph represents acceleration is 0, that is, constant speed. The last part, a straight line graph with negative gradient, represents constant deceleration. In another word, the speed is decreasing. Scalar and vector quantities. Distance and speed are examples of scalar quantities. Scalar quantities have magnitude but no direction. Today you will learn about displacement, velocity, acceleration, which are examples of vector quantities. Vector quantities have magnitude and direction. To note that a particle is a body small enough for its dimension to be ignored. In kinematics, we are going to use the word particle quite often. Differentiation of displacement. In earlier slides, we have mentioned that in a distance time graph, the gradient represents speed. Keeping this principle in mind, let's apply it to a function in t representing displacement. If s is the displacement traveled in time t, and s is a function of t, then the gradient function ds by dt will represent the velocity v at a given instant. V is equal to ds by dt, where s is a function in t. Differentiation of velocity. If v is the velocity in time t, and v is a function of t, then the gradient function dv by dt will represent the acceleration a at a given instant. A is equal to dv by dt, which is equal to second derivative of s, which is d of ds by dt over dt, which is equal to d to the power of 2s divided by dt to the power of 2, where s and v are functions in t. Units of displacement, velocity and acceleration. Units of displacement are meters or kilometers. Units of velocity are meters per second or kilometer per hour. Units of acceleration are meters per second square or kilometer per hour square. A quick recap. From S to get V, we differentiate ds by dt. From V to get A, we differentiate dV by dt. Let's apply this rule to an example. A particle starts from a point O and moves in a straight line so that its distance s meters from O after time t seconds is given by s is equal to 3t squared minus t cubed over 9. Part A, find. First part, its initial velocity and acceleration. Part 2, the time after the start when it comes to a momentary halt. Part 3, its distance from O at that time. Part B, what maximum velocity does it reach before that time? Part C, after what time does the particle pass through O again? S is equal to 3t squared minus t cubed over 9. The initial velocity, v, is when t is equal to 0. v is equal to ds by dt. It is equal to differentiation of 3t squared minus t cubed over 9 with respect to t. v is equal to 6t minus 1/3 t squared. Substituting the value of t is equal to 0 in this equation, we get v is equal to 6 into 0 minus 1/3 into 0 to the square. Evaluating this, we get v is equal to 0. Therefore, initially, it was at rest, no movement. S is equal to 3t squared minus t cubed over 9. v is equal to 6t minus 1/3 t squared. Initial acceleration A is when t is equal to 0. A is equal to dv by dt, which is equal to differentiation of 6t minus 1/3 t squared with respect to t. A is equal to 6 minus 2/3 t. Substituting the value of t is equal to 0 in this equation, we get A is equal to 6 minus 2/3 into 0. Evaluating this, we get A is equal to 6 meters per second square. The time after the start when it comes to a momentary halt. Momentary halt means v is equal to 0. We equate 6t minus 1/3 t squared to 0. Factorize it to get 1/3 t into 18 minus t is equal to 0. T is equal to 0 second at start of a journey, or t is equal to 18 seconds. This is the time after the start when it comes to a momentary halt. Its distance from O at that time. S is equal to 3t squared minus t cubed over 9. Substituting the value of t is equal to 18 in this equation and evaluating this, we get S is equal to 324 meters. What maximum velocity does it reach before that time? Maximum velocity means dv by dt, which is equal to A, is equal to 0. A is equal to 6 minus 2/3 t. 6 minus 2/3 t is equal to 0. Solving this equation, we get t is equal to 9 seconds. Now we substitute this value to get the maximum v. 6 into 9 minus 1/3 9 to the square. Evaluating this, we get the maximum v, which is equal to 27 meters per second. After what time does the particle pass through O again? At O, S is equal to 0. 3t squared minus t cubed over 9 is equal to 0. Factorizing this, we get 1/9 t squared into 27 minus t is equal to 0. Solving, we get t is equal to 0 second. T is equal to 27 seconds. This is the time that the particle passes through O again. Now that we have done an example for you, here are some exercises for you to practice. So students, today you have learned how to apply differentiation to kinematics problems that involve displacement, velocity and acceleration of a particle moving in a straight line with variable or constant acceleration. I hope you have enjoyed it. See you next time.